In this example, we're asked, according to the rational root theorem, what are all possible root or rational roots of the function f of x equals 2x to the power of 6 minus 4x to the third plus x squared minus 6. Well, here's the rational root theorem. In summary of the rational root theorem, all possible roots are given by the factors or the expression p over q, where p comes from the factors of the constant term, so that's the last term without the variable, and q comes from the term of the leading coefficient. So if we look at this, when we want to list all possible rational roots, we're just going to start off by listing the values of p and q. So p is all possible factors of our constant term, which is the 6 on the end here. So the possible ways of factoring 6 are 1 and 6 and 2 and 3. But in addition to just those ones, we have to consider both positive and negative versions. So the possible factors of p are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, because both positive and negative numbers go into the 6. And for the q, we're going to look at the leading coefficient. So that's going to be the 2. So q is going to be composed of all possible factors of 2. And again, we have to take into account both the positive and negatives. So plus minus 2 and plus minus 1. I'm going to write that in ascending order. So plus minus 1 and plus minus 2. And finally, for the actual rational roots, those are the p's over q's, or the possible combinations of it. Basically, we're going to take each possible combination of p and q and write it as a fraction. So the p's are on top, q's are on the bottom. We would start off with 1 over 1. 1 divided by 1 is 1, and of course plus or minus. Next, we're going to go 1 over 2, which is 1/2. So plus or minus 1/2. So if we use the 1, now we're going to use the 2. So 2 over 1. 2 divided by 1 is 2. So plus minus 2. Then 2 divided by 2. 2 divided by 2 is 1, which is already on our list, so we don't have to add it. Now we're going to do our next one. So 3 over 1. 3 divided by 1 is 3. So plus or minus 3. And then 3 over 2, which is just going to be 3/2. So that finishes the 3. Now we just have one more value for p to go through. So we're going to do 6 over 1. 6 over 1 is just 6, so plus or minus 6. And then 6 over 3, 6 divided by 3, or sorry, I was already doing the division. 6 divided by 2, and 6 divided by 2 is 3, which is already on our list. So these are all possible values of p over q. But just to pose a question, how do we find which ones are the actual values of p's and q's? If we look at a graph of this function, so I have one down here, you can see that, well, this one's not a whole number, so that would be hard to tell if it's on that list. And that looks pretty close to being -1 right there, but I'm not sure. So if I pull up a graphing calculator, pull up Desmos here, I already have the equation typed up, and if I click on it, we can see the actual roots, which neither of those are on this list of numbers. So how could we figure that out, though, without a graphing calculator? And that's where either synthetic division comes in or evaluating the polynomial using the possible roots, applying the rational root theorem, which we'll do in the next example. Okay, so in this example, we're asked what are all the complex roots for the polynomial equation 3x to the fourth plus 4x to the third plus 2x squared minus x minus 2. So in order to find the complex roots, we're going to start by finding the rational roots and decreasing the degree of our polynomial with synthetic division. So, just like our first example, we're going to have to figure out the possible rational roots using the p's and q's. So p comes from the possible factors of our last term. The possible factors of 2 are just 1 and 2. And of course, we got to consider both positive and negative versions. And for the possible values of q, that comes from our leading coefficient, which is 3. The ways we can factor 3 are 1 and 3. Of course, we got to consider both positive and negatives. So overall, the actual possible rational roots are the combination of p's over q's. So 1 divided by 1, which is 1. Of course, our plus minus. 2 divided by 1, which is 2. Then we have 1, I forget which ones I did. I did 1 over 1 and 2 over 1. And I guess I have to do 1 over 3, which is 1/3. And 2 over 3, which is 2/3. There isn't a set way you have to go through listing out all the possible combinations. You just got to make sure you get all the combinations. So we've listed all possible combinations. Once we have this, we just have to go through and try to figure out which ones are actual roots or which ones go in evenly. And we can do this in one of two common ways. We can either use synthetic division, which also means we could do long division, or we can use evaluating the function. So I'm going to show you one of each, and then we're going to go through the actual things. So we do have to take a guess as to what one root might be. So I'm going to try positive 1 first. Let's just try positive 1 as our first root and see if that works. So if I try positive 1, we have 3 as our coefficient, 4, 2, -1, and -2. We're not missing any exponents, so I don't need any placeholders. I'm going to drop through this really quickly. We'll multiply and add, multiply and add, multiply and add, multiply and add. So that gives me a remainder of 6, which means 1 is not a root of this polynomial. So I can eliminate positive 1 as a possible root, but I also have to check negative 1. And if I remember right from doing this earlier, I'm pretty sure negative 1 is 1. Let's just try that one real quick. Okay, so we'll drop first number down, multiply, add, multiply, add, multiply, add, and multiply and add. Cool. We do get 0 as a remainder, so 1 is indeed one of the roots. We do have to find the other one. 1 could still be a root, but I don't think it actually is in this case. So we could always try, negative 1 could still be a root, so we can always try dividing by -1 a second time to see if we get, see if it goes in evenly. But I'm pretty sure, if I remember right, it was one of the other numbers. So I'm just going to quickly use the remainder theorem to figure out what is the other one. So I already have the function typed here into Desmos. So I'm just going to quickly figure it out. Let's see, if I try to plug in 2, we don't get 0. Remember the remainder theorem, if it is indeed a factor, will give us 0. And of course, -2 doesn't work. How about 1/3? Yep, so that's 1/2. 1/3, nope. And -1/3? Neither that, so it must be either positive or -2/3. It's got to be one of them. There we go, positive 2/3. So we found one with a remainder of 0. So 2/3 must be it. So we'll try 2/3. And we don't have to go back to the original. We can just use the remainder or the coefficients from our last synthetic division and just continue the process. 3, 1, 1, -2. Dropping our first number down. 2/3 times 3 is 2. Add it up, we get 3. 2/3 times 3 is 2. Add it up, we get 3. 2/3 times 3 is 2. Added up, we get 0. So we do have a remainder of 0. Awesome. So cool. We are now down to a quadratic, or at least we should be. We started off with an x to the 4th, which means after the first successful synthetic division, we would have an x to the 3rd as our leading coefficient. Let's make that red so it stands out a little bit more. And then after our second synthetic division, that would put us down to x squared as our highest power, giving us a quadratic. Now, it's at this point where you can try to factor the polynomial. This particular one I already know doesn't factor, but you can always try to factor and get the roots that way. But since I know for sure it doesn't factor, I'm just going to use quadratic formula to finish finding the rest of the roots. So negative b in this case, a is 3, b is also 3, and c is also 3. They all happen to be 3, which makes plugging stuff in horribly easy, because even if you make a mistake, you got the same thing. Unless you do what I did there. There we go. Minus 4ac, so 3 times 3, all over 2a. There we go. So the same three things I always tell my students to do. Deal with that negative. Plus minus, the square root. If you're using a calculator, just type all this in at once. If we do that, 36 minus 9 is negative 27. Yeah, negative 27. All over 2 times 3, which is 6. Simplify that radical. So negative 1, 9 goes into 27, and 9 times 3. So if we simplify the radical, we have negative 3 plus or minus square root of negative 1 is I. Square root of 9 is 3. And we can't square root the remaining 3. And we see that 3 can go into all three of these numbers, so we'll reduce this fraction, giving us negative 1 plus minus 1i, or just I, radical 3, all over 2. In summary, our four solutions are going to be, and yes, 4 solutions, if you've forgotten, our degree is 4, so that means we should have a total of 4 solutions, or 4 roots. But our 4 solutions are going to be negative 1 plus I radical 3 over 2, negative 1i plus I radical 3, oh my gosh, negative 1 minus I radical 3 over 2. Then the 2 we found when we were doing the synthetic division, the negative 1 and the 2/3. And that does it. So those are all the rational and complex roots for this polynomial. Oh my gosh.